Okay. So, when I was picking out things that I wanted to talk about, not necessarily what was in the textbook that I bought or picked out for this semester, this is one of the things I wanted to hit, probably harder than he hits it. This idea of thunderstorms. So we talked about 10 different cloud types. In one cloud, we talked about 2 cloud types that give you precipitation. Remember, they have the word NIMB in them. And so cumulonimbus clouds are our thunderstorm clouds. When we talk about severe weather, severe means that we have lightning, heavy rain, hail, and or tornadoes. Okay. So the energy, and I'm going to actually add to this line, you guys had a homework question that you just handed in, and actually the energy associated with that makes hurricanes so wicked is the same energy that makes thunderstorms so wicked. And actually that is the latent heat. All latent heat means is basically something's changing phase, like from a solid to a liquid or a liquid to a gas. Latent heat of condensation. Remember we said that, of course, when water condenses, it's going from a vapor to a liquid. That's condensation. And condensation is very, it liberates lots of energy. Condensation is very, what we say, exothermic. So it liberates. Okay. So we need condensation to happen, and then we can maybe have some sort of cumulonimbus cloud with severe weather. So we talked about a chunk of air rising. When we talked about clouds, we said if you get a chunk of air rising, okay, just a chunk of air, not a cloud, but if you get a chunk of air rising, it's going to get as big as a house. And as it gets large, it's going to cool down. Okay, that sort of chunk of air rising, that's actually what we call instability. Okay, unstable. If it's going to rise, it's what we say unstable. We actually talked about 4 ways of getting a chunk of air to rise earlier in your notes. Okay. So I'm going to first break it out by cells, thunderstorm cells, and then we'll talk about how thunderstorm cells can become organized into multiple cells, kind of gang up. Okay, what we call multi-cell thunderstorm systems. So when you isolate it by just a particular little thunderstorm cell, it may or may not be severe weather. Usually, if they're just by themselves, they aren't necessarily severe weather. But they go through these phases. So first they'll be in their cumulus stage, then they'll be in their mature stage, and then they'll be in their dissipating stage. And so I have some figures to kind of go along with that. Just a regular thunderstorm cell. So actually you can see, we just have to take somebody's word for this, that this is not just a regular cumulus cloud. This is actually a cumulonimbus cloud. If we were to look underneath it, it'd be like, the little person down here is like all dark and stuff and getting rained on. Okay? Can you see how crisp this is? And I've heard it described like cauliflower. Okay? The more crisp the top of the cloud, that means it's kind of newly developed or developing. So this is kind of a new guy, and this could actually bring some interesting weather. This would be like more with the mature stage instead of the dissipating stage when it's nice and crisp like that. So the 3 stages look like this. Okay, this is what we call the cumulus stage, and cumulus kind of sounds like the beginning of the cloud type, cumulonimbus, cumulus stage. So we have kind of these arrows with these 3 stages. This red arrow actually is what we call an updraft. The red arrow is an updraft going up. Okay. Actually, anywhere on Earth, we have an ongoing updraft situation. So remember we said that wind is created if air wants to go from a high pressure to a low pressure. That actually creates wind. So honestly, we kind of have an ongoing situation of that because you guys would tell me, I think you told me on a homework, that actually the air is thicker. I'll put an H for thicker air, higher pressure down here, and the air is thinner with a lower pressure up here. So we do kind of, it's a gentle sort of situation, but we do have kind of like an updraft ongoing, okay? That's what we call the vertical updraft. Okay. So as you can get a chunk of air to rise, it will get bigger, and as it gets bigger, it will cool down. And if there's some water vapor in it, it can actually cool down to the point of water condensing. And that's actually the beginnings of either a cloud or a thunderstorm cell. Okay. So this is actually kind of a review term a little bit. We said that you get a chunk of air rising, it'll get bigger and bigger, it'll cool down. We know the rate at which it will cool down actually. And the elevation at which it's cool enough to begin condensing, we actually call that the lifting condensation level. And this is why most cloud bottoms are flat. So in this little figure, I would call the lifting condensation level right about here. Okay, that is the L, lifting condensation level, the LCL. It's actually an elevation, okay, that you needed to go ahead and raise a chunk of air up to get it to cool down enough to go ahead and begin condensation. Now, whether you're going to get a cloud, condensation or not, it kind of depends upon how much water vapor you had in there too. Not just how cool it is, but also the amount of water vapor. So I mentioned kind of the cauliflower crisp, okay? The crisper the edges of the cloud, that means it's more newly to have arrived. And you've seen this before, like if a thunderstorm system is breaking up, you can actually kind of see it, they look kind of more like diffuse, the tops of them. It's like, you're done. You're not going to give us any more. But if they're nice and crisp, you're like, all right, I think you're still building. So this is the middle stage. This is the mature stage, and I have a couple slides on this. But now notice we still have the updraft, the red updraft, but now we also have a blue downdraft, okay, downdraft. And what a downdraft means is kind of what it sounds like. Basically, air is moving down within that cloud. And kind of one of the reasons that air moves down is what's happening at the bottom of the downdraft, it's raining, okay? So I kind of think of it this way. This down here, this precipitation down here actually kind of pulls the air along with it as those raindrops fall, okay? So if falling rain creates a downdraft. So in the mature stage, actually, that's when you're going to find your most interesting weather. Okay. The mature stage, you're going to have if you're going to have a tornado, it's going to be in the mature stage. If you're going to have hail, it's going to be the mature stage. If you get the idea. Lightning, mature stage. So one of the features about, it doesn't have to be a mature stage, but just a cumulonimbus cloud. The thing about a cumulonimbus cloud is it's very deep. Okay, actually it can span the whole troposphere. And on top of the troposphere we have the tropopause, and then we go in the stratosphere, okay? The tropopause actually, it prevents, how do I say this, air doesn't freely move past that tropopause. It's called a lid from the troposphere. So what happens is that cloud kind of tops out at the troposphere, okay, tropopause, top of the troposphere, and it kind of flattens out and it makes an anvil. So can you see the anvil here? The anvil feature would be right, actually I see two anvils, and usually one is longer than the other, okay? The longer one is what we say kind of pointing in the direction that thunderstorm cell is moving, okay? So it has flattened up against we must be shooting up against the tropopause. I'll put T-pause for tropopause, okay, right there. Okay. So the mature stage is where you're going to get your crazy weather, including lightning, crazy precipitation, and actually the mature stage is when you're maybe going to get hail. Now, we don't always get hail with a thunderstorm cell, cumulonimbus cell, but sometimes we do. I wanted to introduce hail because hail is totally different than sleet. Sometimes, and I used to get it more confused than I do now, sometimes I would get sleet confused with hail. Sleet is just basically water, let's see, how do I say it? Probably it fell from the cloud as snow, it melted, and then it refroze. That's sleet, okay? Hail is totally different. Hail is actually, happens as basically kind of a chunk of ice called grapple. Now, you may not have heard of grapple before, it's kind of a weird word. But grapple can exist up there in your clouds, including a cumulonimbus cloud. And the thing that happens with hail is a piece of grapple it's a roller coaster. Can you see that purple line there? That roller coaster that piece of grapple rides, okay? Here's the piece of grapple, and here's kind of the roller coaster. It goes up and down and up and down. And the reason it goes up is because of the updraft. And the reason it becomes down is probably because gravity. It just got big enough to want to fall from the cloud. It catches another updraft, then it falls down. It catches another updraft, and it falls down. So that's your grapple turning into hail. Okay? So now notice that actually the hail, if it's going to fall, will fall where your precipitation is falling, but it creates, kind of all falls at once in what we call a hail shower. So the size of the hail kind of depends upon how strong your updraft is. These red ones are your updraft. If you have a crazy, crazy updraft, okay, kind of an out of control sort of updraft, you can get very large hail. The thing about hail, maybe you've noticed it before, is since it takes so many trips through the cloud, it kind of gets this onion sort of shape. So the middle part is where it started, and it keeps adding a layer as it kind of goes up and down and up and down and up and down. Like, that is so cool. It's cool as long as it doesn't like fall on your car or something like that, right? A lot of times, like the National Weather Service, they in the springtime, they put on these trainer sessions. If you haven't gone to one, I suggest you do. And they just kind of tell you what to look for with severe weather. And the other thing the National Weather Service wants to do is to, here in the Midwest, they want all sorts of eyes on the ground, boots on the ground, to basically call in what you see. National Weather Service has some great, toys to understand what the weather's doing, but they really need people that can call in and tell them what you're seeing. And one of the things they tell you is how big is the hail. Okay, so we had cumulus stage, mature stage, and dissipating stage. And the word dissipating almost sounds like what it is. It kind of peters out. So now notice we don't have the red updraft. We just have a blue downdraft. So we might have precipitation, but it's really kind of wimpy. It's no longer being what we say fed. Remember, it's that the water vapor condensing that kind of feeds your thunderstorm cell. Okay, so this is kind of the end. You still see an anvil up there, but it's kind of a wimpier anvil. Okay, so that's the end. And as we talk about, that was a thunderstorm cell. So that was like a cell. I kind of think of a cell as a circle, right? Okay, so that's just one isolated cell. We have some variations of that, okay? And I'll talk about those. So severe thunderstorms, okay, one of the things I think is interesting, and I don't have the severe thunderstorms. I wish I had the National Weather Service criteria for calling a severe thunderstorm alert, but it's not thunder. I mean, it's not, thunder's the audible part of lightning, right? Just lightning in and of itself will not make the National Weather Service call a thunderstorm warning, okay? It has to be a certain amount of wind speed, certain size of hail, and or has to be known to spawn or create tornadoes. So here we go. There is the thunderstorm mature stage of a thunderstorm cell. Okay. So pointing out a few things. Actually, if you want to put a little star up here and put homework next to it, here in a minute I have homework to hand out to you. Okay, I'll just give it to you now. Don't forget. It's on a slide, but I couldn't see any good shipment homework. So what I want you guys to do is basically sketch this for credit and turn it in on Wednesday. You can even sketch it on this piece of paper. Okay, so mature stage of a thunderstorm cell. Okay, so you see the anvil part. Now, do you see what I mean about the long part of the anvil? Okay, like sometimes we see, to me, anvil and anvil, but this is definitely the long part of the anvil. And this is pointing in the direction that the storm is moving. There's some practical things here. So this is anvil up here. And the long part of the anvil is showing the direction that it's moving. Let's see. Now, this is so cool. If you're one that likes to kind of sit out on your porch and kind of like, oh my gosh, that is a cool weather system coming in, and I'm just going to stay here until I get wet. Have you ever noticed like kind of a breeze, and sometimes a really strong breeze before the storm cloud gets to you? Actually, that's what they call a gust front. Down here at the bottom, it looks blue, but actually if you look at it, it's not, there's no, this right here, pick a different color, this right here, okay, there's no precipitation there. You could be sitting on your rocker, okay, and basically get hit by this gust of air that's coming out. And actually it's associated with that downdraft. So if you have a gust front, that means somewhere nearby it's precipitating quite a bit. The stronger the gust front, the heavier the precipitation. The other thing is a shelf cloud, and I guess it's not labeled, but I'm asking you to label it. Maybe it is. This right here is what I would call, let me pick blue here. This right here is what I would call a shelf cloud. Shelf cloud. Okay, and it kind of juts out in front of the storm, and maybe you've seen those before. Right here, this is a shelf cloud. Okay, and to me, kind of the shelf cloud is created in a sense because of the gust front and also because of something else here. Now you see these red lines? I'm running out of room here. These red lines, this right here, this bit of air going in, okay, going in and up and hopefully, or you know, if you want a thunderstorm, hopefully it's nice, warm, moist air going up, condensing and kind of fueling that thunderstorm cell. That right there actually is what we call inflow. Inflow. And I have a video to show you inflow. So you have a gust front coming out, inflow going in. Can you almost see where the gust front coming out, inflow going in? It kind of doesn't almost seem like your air is going two different directions right there. Actually, that can create what we call a roll cloud, and actually that can be kind of kind of give you some twisties there. So here is the video I picked out. Let's see if it works. Okay, so yep. So for your homework, some of you probably already have it done, but for your homework, that's what I'd like you to sketch. Okay, so we talked about the whole, cumulus stage, mature stage, and dissipating stage for a normal thunderstorm cell. But not all thunderstorm cells are created equally. Now, if you've probably heard the weatherman say that we've got a supercell in the area, okay, supercells get everybody, supercell thunderstorm cells get everybody's adrenaline going for a good reason, okay? Supercells are larger. This actually is an aerial view of a couple supercells, okay, where we're actually looking at cloud tops here. So here's one thunderstorm cell, another thunderstorm cell. It kind of reminds me when we looked at hurricanes, where you can actually look at the tops of the clouds and you're like, oh my gosh. They can be like very large, okay, 12 to 30 miles for one blob, and they last a long time, supercells. So that's not good. So this is actually then is a diagram of a supercell thunderstorm cell. Okay. Now notice it's a little bit different than what we looked at before. If you look at it, it's got some very similar features, but let's see where it's similar and where it's different. Okay. Notice it's got an anvil. Okay. One of the things actually, not just supercells, but all thunderstorm cells can have, and I didn't emphasize it this semester for you, but if they go past, they flatten out at the tropopause, and if they shoot up in the stratosphere, actually they can create what's called overshooting tops. Okay, so the overshooting top is in the stratosphere. Stratosphere. And again, this doesn't have to be with supercells, but it could be just with regular. If you see overshooting tops, then you're like, oh, okay, then that means that it's really tall. It's got a lot of instability. Now, one of the big things you see that's different is this, what we call mesocyclone. This mesocyclone is a twisty thing. Okay, if like twisty tornado, you're right. Okay, so supercells, if they do spawn a tornado, the tornado actually comes from this mesocyclone. Now remember, this thing is large, and so this mesocyclone is a big kind of large thing going blah, 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 kind of a thing going, circulating, okay? It actually is associated with the updraft, okay, because it's red. But you see the blue there? The blue is your downdraft again. Okay, so you have an updraft like we saw before, but now the updraft and the downdraft actually are kind of getting wrapped, what we say, wrapped around each other in the mesocyclone. Okay, so it's definitely a little more complex than we saw before. Okay, you see the downdraft gust front that we talked about before, okay? So if you are going to have a tornado, like I said, it's going to, this big rotation thing, this mesocyclone, and meteorologists will actually talk about this mesocyclone sometimes. Okay, it's not a tornado, but tornadoes drop out from it. Okay. So supercells then can give you hail, lightning, intense precipitation, and tornadoes can. Okay, they last a long time, and sometimes it seems like around here we'll have a series of thunderstorms, like bunches of several cells that are, supercells all at once. It seems like that is bad. Okay. So speaking of, when the thunderstorm cells gang up, we call them multi-cell thunderstorms. Okay. So this is not just your onesie, but it's multiple ones. And there's two types of situations where you can actually have more than one thunderstorm cell kind of doing its thing. This is probably, well, actually they're both kind of common. If you've heard of a squall line, okay, a squall line is basically you look out and you see thunderstorm, 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 like an army coming towards you. That is a squall line of thunderstorms. And probably, honestly, you basically have a cold front that is scraping, cold air is scraping the ground and pushing warm air up and creating a squall line of thunderstorms. Usually a cold front, maybe a dry line. The other one is a blobby, not a line of them, but it's a blob of basically individual thunderstorm cells working together. They call those mesoscale convective complexes. Like if you live in a complex, you live where a lot of people live. Okay, so this is just a complex of thunderstorms. So I know you can't, doesn't look like it, but over here on this image, like this right here, actually has multiple thunderstorm cells working, okay? Mesoscale convective complex. These mesoscale convective complexes, these are actually what we get in our nighttime thunderstorms. That's what I think of. Haven't you ever looked at the forecast, gone to bed, and you're like, oh, it's going to be one of those? Okay. So lightning. Remember, lightning occurs in thunderstorm in its mature stage. And actually, I kind of want to talk about the different types of lightning. I'm not going to really talk about how lightning forms, per se. But actually, most lightning, notice the 80%, most lightning actually is from cloud to cloud. And I'm not going to talk about it much, but you guys are probably pretty good with lightning is basically electricity is going from one place to another. It's like electricity in our home when we plug something in. You plug something in, electricity flows. Okay, that's the same thing what's happening to create lightning. So most of it actually is what we call sheet lightning, not to be confused with, on the next page I have something called heat lightning. Sheet lightning and heat lightning are related, but okay, so most lightning won't get you. That 20% that will get you, honestly, is worth going indoors for, okay? In particular, like if you are outdoors and there are some sort of lightning going on either near you or kind of, you can still hear it. Like I said, if you can hear it, it can reach you. And if your hair starts tingling or something like that, what's happening probably is that the lightning is interacting with you, and so you might be its next target. So I'm not saying you'll always feel that little hair standing on it. So 20% is the type that goes from a cloud to the ground. The taller the object, the more likely it is to get struck. So with lightning, we have thunder. Okay, so with lightning we have thunder. I'm going to kind of tell you, we don't always hear the thunder that's associated with lightning, but the thunder's always there. And I mentioned that lightning is basically electricity going from point A to point B, whether it's like between clouds or from cloud to ground. Okay, so when electricity does that, basically it heats the air in its vicinity of the path of the lightning bolt, and the air is heated so fast that it expands, because that basically those air molecules get going really fast and they move out, and they go faster than the speed of sound. Basically, they push out faster than the speed of sound. They create a sonic boom. Okay, and that's what we call thunder. Okay, so one of the things about it, and I think we talked about this earlier, remember we said that we had the concept of a light year? Okay, how far away is that star? Well, it's 4 light years away. What does that mean? It means it takes, once that star shines light, it takes 4 years for that light to get to us. So light travels at a certain speed, okay? But it's faster than sound travels, okay? Sound is not in and of itself, sound is not an electromagnetic radiation. Sound is not a cousin, okay? So sound travels more slowly. So basically, that's why you see the flash, and then later you hear the thunder, okay? And if you've ever heard this adage, actually you can count the delay, the seconds of the delay. So you see the flash, okay, you hear the thunder. I looked it up, and I've seen different numbers, but I've kind of come up with 5. So divide by 5. So if we got, we see the lightning, and then 15 seconds later, okay, we hear the thunder, then you take 15 seconds, divide by 5, and you get 3 miles. So that lightning bolt's about 3 miles away, okay? So that's to say then, if you see the lightning and you hear the thunder in about 1 second, okay, then it's about like what, 1 divided by 5, or 1/20th of a mile away. And you're like me, those ones where there's not much of a delay, they're really close, they have a different quality of sound to them. So actually I kind of have something along those lines. You hear a thunder clap to me is that, and that actually, the crisp thunder clap means it's probably very close. And then we kind of have the rolling thunder. And I think if you're in a region that has kind of hills and that sort of sound thing, the rolling thunder is basically where you see the lightning, it might be 10, 15, 20 seconds later, you hear the thunder, and it goes whoa, 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 okay? That just means it's kind of bouncing around. So I said that sheet lightning is not the same thing as heat lightning. So one of the things I want you to know, this unit, this part of the material, is what is heat lightning? So heat lightning comes oftentimes like in our muggy summer days, which will be here before we know it, okay? So heat lightning actually is where you see the flashes off in the distance, but you don't hear it. And the reason for that is if you were closer to it, you would hear it like normal thunder. But the thing is that the thunder it doesn't have enough energy to get to you. So the light gets to you, but the thunder basically breaks up before it gets to you. And kind of the breaking point is about 12 miles away or so. So 12 miles or further, you're going to see lightning, okay, but you're not going to hear the thunder. I said it's kind of related to sheet lightning, because sheet lightning, remember, is that 80% of lightning that basically is from cloud to cloud or within the same cloud, okay? To me, this sort of distant lightning, you're most likely to see is going to be that sheet lightning. So heat lightning is probably going to be sheet lightning. But heat lightning, like I said, is far enough away that you don't hear the thunder. Okay, so tornadoes. I've got a little video here to show you. So remember, supercell thunderstorms oftentimes will give you tornadoes because they have that mesocyclone kind of in the middle of the supercell thunderstorms. You can get tornadoes from regular thunderstorm cells too, though. We talked about isobars. Remember, we said that if you're looking at a weather map, and let's see if I can draw. I haven't drawn one of these. There's my Florida. Oh my gosh. Here's my, Mexico. Okay, and Canada's up there, right? If we look at a weather map, and we see an H here, that's of course a high pressure cyclone. Okay, we can see this is going to be my isobars. Okay, if we see on the same weather map, and they alternate, H's oftentimes alternate with lows. If you see, this is going to be my point. If these are isobars and you see those isobars nice and tight, that means that you don't have to go very far to have a change in pressure. Those are all just different pressures. Okay, so we have tight changes that brings you crazy wind. So actually, that's what's happening with regard to a tornado. So if you were to look at a tornado, and they kind of take on different shapes, down here at the bottom is a low pressure, okay, and then scooting out from that low, okay, actually the crazy wind associated with a tornado is because of the tight differences in the pressures. Okay, so tornadoes. They vary in sizes and intensities and how long they last, okay? But the problem with tornadoes compared to hurricanes is they don't last very long. You say, how's that a problem? Well, that means that they come out of nowhere, basically, and then they don't last long enough to get some really good science about it. If you've seen the movie Twister in here, everybody's seen Twister, hopefully. Okay. They were trying to get some good scientific data, and they continue to try to get some good scientific data with tornadoes. Some years are worse for tornadoes than others, and it kind of alternates because of kind of the overall atmosphere of the globe. But if you have a year that has mild for hurricanes, it usually favors tornadoes, and if it's crazy for hurricanes, it usually disfavors tornadoes. This one is kind of what I would call a wedge. Doesn't that look like a wedge? And this is more like a rope tornado. Okay. So we're going to look at how you classify tornadoes, and some of you guys probably already know it's the Fujita scale. Now it's the EF, or Enhanced Fujita scale, which is similar to the F scale. An F5 or EF5 is the worst, and EF0 is the best. One of the things about tornadoes is even if you are trying to help the National Weather Service and be a spotter to tell them where the tornadoes and where the hail is and how big it is and how strong the wind is, they tell you don't go out at nighttime. Don't go chasing tornadoes at night. Your best bet of seeing a tornado at night, honestly, is if it interacts with some sort of electrical pole. You're like, oh, it just took down an electrical pole. You're like, there it is. So not a good thing. So here are kind of some extreme tornado situations. The world's deadliest tornado, and I'm going to show you in a minute where tornadoes form. Most tornadoes are like North America just gets lots of tornadoes. But actually the worst one wasn't even in North America. Sometimes they come in a tornado outbreak. You've probably heard that before. Just kind of the conditions are ripe to create one thunderstorm cell that spawns a tornado, to create lots of thunderstorm cells, maybe even supercells that spawn tornadoes. Right. So this actually is the aftermath of, let's see, these two tornadoes were in Tennessee and Kentucky, were part of the same outbreak. A big difference about classifying tornadoes versus hurricanes is tornadoes, you don't classify them while in the act of being a tornado. You basically go visit it afterwards, get an estimate on how fast the wind was to create those situations, and then give it an EF value. So tornadoes are not well understood. But actually, we think that it sort of has some sort of kind of rolling sort of situation going on at the ground. That roll then gets lifted up, and you probably recognize this sort of mesocyclone maybe within your cumulonimbus cloud. You know it's a cumulonimbus cloud. It's got the anvil feature. These are the overshooting tops into the stratosphere. Okay. So this says only TS stands for thunderstorms. So if you have 100 thunderstorms, about one of them is going to give you a tornado. This one over here, okay, this right here, you can actually not even see the top of the thunderstorm cell. But down here, we would all probably say, well, there's some sort of activity there. Basically, all a tornado is moving air. A tornado is just a bunch of moving air. So you're like, how are you going to see moving air? Well, you see moving air oftentimes when it picks up debris. So when it hits the ground and starts kind of picking up dust, debris, cows, okay, then you know actually you can see where the tornado is. So invisible tornadoes are a thing, you know. So you see, this maybe looks familiar with our cumulonimbus cloud, our mature thunderstorm cell. Okay, here again is the anvil, the long part of the anvil. We kind of have a back part of the anvil, so we know it's going in this direction. Okay, they call it penetrating tops, the same thing as overshooting tops into the stratosphere. We're not showing you the updraft and the downdraft, but the updraft has to be ahead of the storm, okay, and the downdraft actually is where you see the heavy rain. Mesocyclone is probably whipping the updraft and the downdraft down together. Now this does say one other thing. So there's this feature called a wall cloud, and you don't always see a wall cloud, but a wall cloud is, okay, so basically you usually kind of have a nice flat bottom to your thunderstorm cell, okay? Extending from the bottom is kind of a little cylinder of cloud, and that actually is your wall cloud. And so they will tell you in spotter training, the National Weather Service will say, if that wall cloud is rotating, and it doesn't have to be rotating fast, spinning, actually, that is where you want to look for your tornado. So the wall clouds are kind of a precursor or associated with the tornado dropping down from it. So how do we categorize them? From 0 to 5. Okay, 0 is the weakest, 5 is the strongest. I don't have a slide on it, but if you've ever heard of like water spouts out there in large bodies of water, those are usually kind of an EF0 kind of tornado. There are not very many strong tornadoes. Okay, so by strong, if strong, we're going for an F or EF4, EF5. Only about 2% of all tornadoes are that strong, but the EF4, EF5s account for 70% of the people who lose their lives. So you've probably heard of Tornado Alley, right? And I looked up on the internet, and it kind of people describe it differently, but Tornado Alley is kind of, if you look for the kind of the hot spots here, okay. Where do tornadoes occur? Let's see. As I've drawn that, I'm trying to see, where are we? I don't think we're even in Tornado Alley. Are we right here, aren't we? Yep. So remember I said that it looks like North America basically says tornadoes come drop on me, right? So this actually is worldwide. Where do the tornadoes happen? And notice each dot is actually a certain number of tornadoes. So we definitely have our fair share of tornadoes. And I've read the explanation for that is, if I draw these, that is the Rocky Mountains, and if I draw this, that's the old Appalachian Mountains. So actually it's kind of those mountain ranges over our land mass that kind of creates the conditions that work well for basically warm air and cold air meeting and kind of doing its thing. Unfortunately. So, tornadoes. I mentioned lightning. If you hear lightning, if you hear thunder, it's time to seek shelter. Okay, thunder doesn't kill people. Lightning kills a lot of people every year, probably more than tornadoes. But tornadoes, you need to obviously respect too. There are different tornado shelters. Otherwise, you get into the center of your home, okay? Feel free to grab a mattress, put it over your head. That's what I tell my mom to do. Okay. Okay, so tornadoes. I'm going to kind of finish up by kind of letting you know things that you might see if there are tornadoes in the area, what the weathermen might be talking about. Let's hold these last few slides until Wednesday. So Wednesday, I'm going to actually show you couple of videos of tornadoes, and then do these couple of slides, and then we'll have time to do a review. Okay?